It's an honor to introduce Neville Hogan, professor in mechanical engineering and also an appointment as professor in brain and cognitive sciences. Neville is an almost all-time MITer. You did your master's and PhD and faculty at MIT, and has received many, many awards. So it's very difficult to do sort of honor to those, but maybe one thing that I would like to highlight is that has received career awards and medals in fields like mechanical engineering, controls, biology, medicine, which is kind of sort of paints like an interesting picture for his research, which sort of focuses with fundamental contributions in both the control of robotic manipulators, but also in understanding how in Earth, like, do humans get to do that so well and make it look so easy. So today, Neville will talk about human behavior and dexterity. And he will most likely use the word impedance a couple of times.
I'm shocked.
But it boils down to the fact that we show this amazing dexterous behavior when there's so many intrinsic limitations to what we think we were supposed to be able to do. And one of the things that I like about his abstract is it sort of paints a very nice, simple picture of how that could be done. It's sort of superposition of these more simpler behaviors, which he calls like workarounds that deal with the computational and mechanical aspects of generating that complexity, which to me is it's interesting because while often it seems hopeless to be able to replicate the amazing things that we can do, it sort of brings a little bit of hope that maybe it's not that complicated. And I just wanted to finish with one thing, which is I realized today that Neville started his faculty position at MIT in 1979, which, if I'm counting right, that makes his 40th anniversary as faculty at MIT.
Thank you for reminding me that I'm old.
Of huge research contributions and service. But then there's the parallel question, which is, after 40 years of research, where are we today?
Boy, that's a tough introduction. Thank you. Thank you for the introduction. Thank you for the opportunity to speak, and thank you for showing up. I'm going to wind up giving you a sample of things that I've worked on with numerous colleagues. So in case I forget, what I'm going to present is not so much my work as work I've been involved with colleagues like Hermano Krebs, who's there in the audience, and Dagmar Sternad and others. So the key question is, how come we're so good? So this is not the most recent video, but that's an example of robot soccer, and I use that. And I'm not criticizing. I think this is great stuff to get students engaged, and it solves hard problems. But you compare that with human soccer, and it's no contest, right? But you have to remember, and people often don't, is that the human is vastly more complex than any of the robots that we have today. Typically, it's 200 plus degrees of freedom and 600 plus actuators. We have feedback loop delays that are on the order of at least 100 milliseconds, maybe more like 200. We have actuators that are slow. Muscles never go above about 3 to 5 hertz, well below 10. And communication. I think it's fair to estimate electronic communication as being about 10 to the 8 meters a second. Neurons communicate at most about 100 meters a second, about 1 million times slower. So the system is slow, and yet we get this spectacular performance. Well, when you have delays and slow responses, it's okay. We can't rely completely on reactive control. So instead, that implies we're going to do some sort of predictive control, like model predictive control. And this makes good sense. And it's now showing up. It originally was developed in chemical engineering, but it's now showing up as a viable approach to control robots. And the idea is that you do finite look-ahead optimal control, and you keep observing the system state. One of the key things about this, however, is that the prediction requires some sort of an internal model, a representation of the system. And there's some evidence that at least the cerebellum, that's your second processor, the brain below the brain, that the cerebellum is involved in internal models. It's one of a number of structures. But there's a problem. If you go to optimize, do prediction based on optimization, that approach is profoundly vulnerable to Bellman's curse of dimensionality. That is, the complexity of the computation problem grows exponentially with the number of time steps and the number of degrees of freedom, and that's a hard problem. So how complex are the things that humans can manage? This is April Choi playing Jenga with a whip, right? There's a soundtrack, but I won't run it. And that's pretty good, isn't it? Now think about it. How complex is the object that she's manipulating? Now I don't know if she's going to win the Jenga, but never mind. This is another young man. This is Adam Winrich. He's able to knock a cap off a bottle. This is a card holding an ice cube. He's able to hit the card and let the ice cube drop in. So this is pretty good, and this is with a whip. I think we have, yeah, this is Eugenia Capanina, gymnast who does ribbon gymnastics. Now notice that not only is she managing all of her body, oh, and by the way, watch her hands. She's very careful about the pose of her hands. She's managing all those degrees of freedom, plus this flexible object, this ribbon, and it's a long ribbon. Now you think about this, if we were to develop a engineering style model of what's going on here, either in the bullwhip or the gymnast ribbon, these are flexible objects. In the bullwhip, it's got non-uniform, non-isotropic mechanical properties interacting with a compressible gas. And if you crack the whip, that's going up to the supersonic regime. So you need partial differential equations, and they are hard to solve in real time just by themselves. Now you're going to make that part of an optimization routine. I don't think you have partial differential equations in your cerebellum. So what are the alternatives? Well, the alternative that my colleagues and I, particularly Dagmar Stonert, have been working on is the notion of what we're calling dynamic primitives. And I probably have to explain that a bit. So the key idea is that we can't rely on reactive control. We have to find some way to work around that. So the primitive dynamic behaviors we're referring to here are things that are attractors that come out of the low-level neuromechanical system. So but when I say attractor, I mean in the sense of nonlinear dynamics. And so you could have a point attractor to manage equilibrium, a limit cycle to manage rhythmic actions, even a trajectory can be an attractor. And I would argue that impedance or interactive behavior can also be an attractor. And this is the notion of dynamic motion primitives has been around for quite some time. Ake Eisbert and Stefan Schall have worked heavily on it. We're thinking to take this idea and extend it to include interactive dynamics. So a reasonable question is, well, how would these dynamic primitives help? Well, the idea is that if you have access to these dynamic entities, you could evoke them with minimal central control. So you could sort of fire down a signal, let behavior fall out. It's not fire and forget, but it's fire and monitor and maybe add corrections later. So you reduce the need for continuous intervention. And I would argue that that's the reason why I'm sure you've all experienced the fact that if you are able to manage some highly skilled behavior like playing tennis, hitting a golf club, or swinging a baseball bat, if you think about what you're doing, you probably are not going to do it as well as you can. You really have to, for example, with a baseball swing, you launch it, you don't try to correct it because you're going to mess it up. And basically, I think what's going on there is that you're interrupting, and you don't need to. Yet at the same time, if you launch these behaviors, each of them could itself, each primitive dynamic behavior could be a highly dynamic behavior. So this is the basic idea. Is there any evidence to support this? Answer is yes. This is early work. This is work done primarily in collaboration with Hermano Krebs. And this is where we developed robots that we were able to make good enough at physical interaction with people to have the robot provide physical therapy for people recovering after a stroke. That's a long story. I don't have time to go into all of it here, but among the things that we were able to do is because you've got a robot involved with a human who's recovering after a stroke, you also have all of the instrumentation and computation to record what they're doing. And as a result of that, we were able to get the first ever kinematic record of what people actually, how people move when they're recovering. And what I'm showing you here, this top panel here, This is the behavior of a lady at 6 weeks post-stroke. And in this particular session, we provide therapy with the robot. And then from time to time, we do evaluation sessions where the robot just goes along for the ride. And this is a highly backdrivable robot, so it's basically a kind of large mouse that the person is using. This is week 6 post-stroke. This is the first time this lady actually began to move. The first week this lady began to move. And we've asked her to draw a circle, and that's her circle. Now, it's not a very circular circle, but that's movement, and this is big progress for her. The other thing to see is you'll see how it's broken up. It's like these corners in it. This is the speed profile along that path. And you'll see that we have these bumps that is, it moves and stops and moves and stops altogether there. So the behavior is clearly fragmented, right? This now, we come along and same lady at week 11 post-stroke. Again, this is her circle. It's still not circular, but it's a whole lot better than it used to be. And the speed profile, now there's still fluctuations in it, but it's much less. For example, it doesn't go all the way down to 0, much less stopping. So the earliest recovering behavior that we see from patients recovering after a stroke are fragmented. They've got these pieces in them. Not only that, but when you look at, this is one of our early studies, we looked at 20 stroke patients. One of them didn't recover, so we have data from 19 stroke patients. That's 19 completely different strokes, meaning that the extent of neural damage is very different. And then what you do is you find the first movements that they make, locate these bumps, these bumps in the speed profile, and extract them. And what you find when you do that, locate the speed peaks, normalize them, fit them to a beta function. The beta function was chosen just as a convenience. It's a 2-parameter family, nothing more to it than that. What you find is that the shape parameters are the same they're within 10% for all these subjects. This is for all of the little velocity peaks that we find in all of the 19 subjects, despite the fact that they have vastly different neural damage. So the speed profile of these fragments doesn't vary. With the lesion, I can tell you about what does vary, but the other thing that's interesting is if you now follow subjects as they go through therapy. This is a sample of first therapy day, last therapy day. The heavy line is the measured behavior. The little light lines are stereotype submovements that we fit to that data. The submovements in this case, we assume that they were support-bounded log normal functions. That's just, it's kind of like a Gaussian, but it can be skewed and it can be platykurtic or mesokurtic. And so what you find in general is that this is for a study of, I think this was 31 patients, if I recall, Eva. So what you find is that as they get better, they make fewer sub-movements. Each sub-movement is longer in duration, higher in peak velocity, and they're more completely blended together. And there's some evidence that a similar thing is found in the kinematic patterns of infant reaching, although I'm less sure about that. This is older data. So this clearly supports the idea that there are at least these fragmentary movements, but they're actually highly stereotyped, and they're not just random pulses, they're shaped movements. Okay. Well, as I said, others have looked at this idea of dynamic motion primitives, but I think that the motion is good, but not enough. You also have to look at interaction, physical interaction, and there you need to look at, for example, mechanical impedance. Now, there's a subtlety here that this may be obvious to you. If it is, I apologize for boring you. If it's not, pay attention. There are two different domains here. So I've seen a lot of work in robotics on motion planning, and this is interesting and valuable work, but that's in the domain of information processing. And the constraints in information processes are basically that you have to have temporal causality, that you can't have the output before the input, and the quantity should be bounded. And as far as I know, that's it. No further constraints. Now I go look at physical interaction between me and an object. That's in the domain of mechanical physics. It's the domain that I call energy processing. And the reason I say that is because if you keep track of energy, that's how you understand dynamics in all domains. So if I go look at energy processing, now I've got a whole stack of other constraints. Not only do I have to have temporal causality and boundedness, but I have to have things like energy conservation, entropy production, and if I have no forces, I've got to have momentum conservation, and on and on and on. So I need to find a representation that properly blends together these two very different domains. And although I'm not a computer scientist, I think that representation is one of the keys to be able to actually do things in a computer that can then be mapped out to practical applications in robots. So how do we represent the combination? So my suggestion is that what we do is we go back to classical electrical circuit theory and repurpose the equivalent electric circuit. Everybody knows what an equivalent circuit is? You should. There's the Thevenin equivalent circuit and there's the Norton equivalent circuit. These are very old ideas. This is Léon Charles Thevenin. We Americans associate him with it. He was scooped by about 50 years by Hermann von Helmholtz, who came up with the idea much earlier. There's a very nice paper by Johnson on the voltage source equivalent circuit. This is Edward Lorian Norton. He's of the Norton equivalent circuit, the one with the current source. In the same month of the same year, 1926, Meyer and Norton published the Norton equivalent, what we call the Norton equivalent circuit, and in extremely obscure journals, right? So the idea was in the air. And this is Oliver Hebeseid, and he was the one who took the core idea of the equivalent, the Thevenin equivalent circuit and generalized it to things with dynamics, and he's the one who coined the words of impedance and admittance and appedance and so on. There's a whole stack of words that he came up with. So this is an old idea. Why would you bother repurposing it? Well, I would argue that there's two key benefits that you get from an equivalent circuit. One is that you take an arbitrarily complex system and you map it into a functionally equivalent form that is much simpler. So I can take, for example, say a stereo amplifier. And there's all that complicated electronic stuff on the inside. But at the place where I'm going to plug in my speaker, I don't care. I need an output impedance, and I need a voltage source. That's it. I can summarize the entire behavior of the complex object as essentially an equivalent, a Thevenin equivalent circuit. So the simpler form but function equivalent is extremely valuable. The other thing that's often perhaps not as well recognized is that both of the components of my equivalent circuit can be identified unambiguously just from experiments made at the place where I'm interacting with the system. So in theory, you can go into the output port of your stereo amplifier and measure both the equivalent source and the equivalent impedance just from measurements. Now, you want to be careful when you do that because you'll blow out the transistors if you do it in a naive way, but it can be done. So for linear systems, these equivalent circuits serve as sort of interface elements because the source element, like the Thevenin equivalent source, that's describing the forward path dynamics sort of in the information domain. It's independent of interaction. On the other hand, the equivalent resistance or impedance describes the interactive dynamics, which is independent of the forward path dynamics. So this sounds promising. Can we map that over to nonlinear systems? And I will argue and try to show you that, yes, you can, with some limitations. So basically, I'm arguing that the architecture of the equivalent network has an equivalent resistance, but it could be nonlinear and dynamic. It's composed of these primitive impedances. I've got an equivalent source term, which is in the information domain. It describes the forward path dynamics, and it's composed of motion primitives. And what I want to emphasize is that I'm including nonlinear dynamics in this part and this part. And I think this is kind of like a sort of a neoclassical approach, and that is I'm trying to use concepts from circuit theory, but I'm not limiting myself to linear circuits. Is that valuable? We'll see. So what's the relevance here? How does this relate to complexity? Okay, well, to recap, an equivalent electric circuit, it masks internal complexity. And this actually fits with what I know about biological systems. So you go pick up any textbook you want on biomechanics or physiology or neural control, and the internal complexity of biology is just mind-boggling, just astonishingly complex. Yet, when you go make measurements, and we have, basically you get second-order behavior in each degree of freedom. Maybe if you push hard, you'll be able to find third-order behavior, for example, in the dynamics of your lower limb. We've never seen a case where the dynamic behavior was as high as fourth order. So I got this complicated system, but externally it looks simple. Sounds a bit like what we would describe with an equivalent circuit. Another important point is that equivalent electrical circuits enable modularity without giving up on dynamics of physics. I don't know if this is clear, but for example, if I stay in the domain of information processing or signal processing, I can have cascade connections, right? This block talks to that block, talks to that block. That's fine, but you can't, that description cannot be consistent with energy conservation. I can have parallel connections and feedback connections, but not cascade connections in the energy domain. So if I have an equivalent circuit, as long as I have these interactive terms, the impedances or resistances, I can respect that. So the idea here is that if I take these nonlinear equivalent networks, I can extend both of these benefits to nonlinear dynamic systems. And what this gives you is, think about it this way. If I look at robot mechanisms, they're fundamentally non-modular. I can't just look at the wrist separately and the elbow separately and the shoulder separately, because they're coupled together, and the coupling is fundamental. However, if I go look at the nonlinear equivalent networks, they enable a certain degree of modularity. So I can develop control modules for arm, wrist, finger, trunk, leg, foot, etc., and add them up. Can I really add them up? Well, with students, I've been exploring these concepts using Baxter. We have a copy of Baxter. I think it was Daniela said Baxter is a lovable, wasn't that the term that she used? Baxter is not the most precise of robots. But it works. So a key thing here is to recognize that impedances, they superimpose linearly even if the impedances themselves are nonlinear, right? So that's what enables controller construction by combining these primitives. So let me walk through an example. Let's suppose I have a desired endpoint stiffness, which I've written down here. And this doesn't have to be linear. I could, for example, make it nonlinear. It doesn't really matter. And I might want to do that if I wanted to limit forces by saturation. It's straightforward to generalize to dynamic terms. I'm not going to do it here. The main thing I need is something that gives me a motion deviation from a nominal determines a force. If you give me the kinematic equations, I can map that to a configuration space. If I have good torque control, which I'm assuming, this gives me a computable control law. And you'll notice that I don't need inverse kinematics, and so this is going to work at singularities. But of course, it doesn't really affect null space motion. So if I have more than the 6 degrees of freedom of the end effector, this doesn't say anything about them. Well, how do I manage redundancy? One way is to say, okay, well, suppose I was to consider a separate controller that in joint space or in configuration space establishes a stiffness relative to a nominal position. And I make sure that this stiffness K is positive definite. And again, I can generalize it to dynamic impedance if you wish. Now all I do is I just add up the controllers. I say, okay, this is my term for the end effector, this is my term for the joint, stick them together, no inverse kinematics, and it works at singularities. And interestingly enough, my choice of this stiffness or of the nominal configuration actually implements a synergy. So if I have the endpoint moving around, this will pattern the relative motions of the degrees of freedom. A big advantage of this is, remember, it's compositional, so I can easily extend this to 2 or more arms. I can, if I have arms connected to a common endpoint or interacting with a common object, just add up the forces. Simple as that. The controller becomes a simple sum of components, and I don't know whether this is true, but I'm curious to know if this would facilitate parallel computation. And I also remember I don't need to invert kinematics ever, which means I don't need to invert closed chain kinematics, which is so. Excuse me. So I would argue that this taking advantage of compositionality may facilitate or ease the scale up to lots of degrees of freedom. So we've applied this to have Baxter do shoe shining. And what Baxter does is, first of all, reaches for this cloth. That, there's no vision system involved here. The cloth was in a previously known location. Then Baxter applies an impedance that stretches the cloth. Then Baxter reduces the vertical impedance a little bit, moves down to manage contact, and then just superimposes an oscillation on top of that. And this is done as a sequence of modules, each of which is described as essentially an impedance. basically a stiffness with a little bit of damping added in. And I want you to notice things like, in this case, for example, we're dealing with a flexible object. Modeling that flexible object would be challenging. We don't bother. We don't have to. We're dealing with multi-arm coordination, 14 degrees of freedom all told. Not a big deal. We have contact and non-contact phases. It's not a problem. The impedance basically takes care of that for you. So this is a demonstration that at least the approach can be made to work in some examples. Another point that I wanted to stress is, remember I said that you don't have to do inverse kinematics. So here we've got a real closed chain, because that's a piece of aluminum bolted out of the end of Baxter. So that's, you might argue that with the cloth, well, it wasn't really closed chain because you could move a bit. Here you can't. But Baxter is able to go all the way into and out of singularity, right, with no obvious difficulty in it. But one of the things I find interesting is it clear how it comes out? I can imagine going into singularity is easy, right? How do you come out? Well, basically, the configuration space is biased towards a particular configuration. That's what the joint space stiffness does. So no inverse kinematics, works into singularities. You can combine pieces. Seems promising. But there's no free lunch, right? Is that Murphy's law or a corollary of Murphy's law? Anyway, these dynamic primitives might simplify programming, but they also imply that there's some performance limitations. And that's one of the things that with colleagues like Dagmar Sternad we've been looking at. And here's one, for example. This is one of a number that we've found. So the idea is that these oscillations, rhythmic behaviors, sub-movements, they have limited sets of preferred timescales. And in particular, there's evidence that humans can't perceive rhythm at a frequency lower than about 0.5 hertz. So if I say, okay, that's part of rhythmic behavior. Wait 10 seconds. That's not rhythmic, right? So yes, you can count your way into timing that, but to make something seem rhythmic, it has to stay within a certain narrow frequency range. So that says that, and a similar thing is true, by the way, for sub-movements, and we think something similar is happening with impedances, but we don't know that yet. So if we have this limited time scale, then that should say that the slower movements should be challenging. So the particular experiment that we did was, this is another one of my former students. We had subjects simply, they're holding, this thing he's holding is a magnetic motion capture. It's a tube with a magnetic motion capture head on top of it. Subjects are asked to move between two large targets in time with a metronome, and they're told to move smoothly and don't stop. So you basically move smoothly back and forth, don't stop. But then we slow down the metronome. So we start with a period of 1 second, progressively slow it down to a period of 6 seconds. So now the movement has to take 6 seconds to go back and forth, and you're supposed to stay in time with the metronome. So here, subjects were able to perform the task. That's one subject. We extracted the individual periods, the cycle times. One subject, that's an average of all subjects, and I don't know if you can see it, but there's a gray band around that. That's the one standard error. So subjects could do the task. But what they couldn't do is not stop. So no matter what, this is the dwell time from a single subject. This is the average the ensemble dwell time from all of our subjects. And you can see there's some noise in our extraction, but it's not that bad. We get a very large increase in dwell time. So even though there's no mechanical reason why they have to stop, by the way we replicated, there was a concern that, well, maybe there's static friction involved. I don't buy it, but we checked anyway by having the subjects do this in air. Same result. There's no friction, there's no static friction in the biological system. There's no reason why you should stop, and yet subjects do. Subjects can't not stop at the ends. And if you look at what's going on, this is what's happening. The green traces are the actual measured movement velocity for the up in the top row is the behavior in the initial the epoch where there was just the 1 second period. The bottom row is in the epoch where you had 6 seconds, and the middle row is in the transitions. And what you can see is that the velocity is getting bumpier and rougher as you slow down, and it's not just the roughness due to the sensor noise. Now we take that data, the dashed lines here are, we fit a sinusoid to each half of the cycle, and over here we fit these support-bounded log normal shapes to it as a means of finding out how many submovements are in there. And what you find is that we take the movement speed profile, fit it to support-bounded log normal submovement shapes, and count the number of submovements. The algorithm fits a submovement, checks if adding a second submovement would improve the fit, keeps doing that until the improvement drops by adding another submovement, drops below 1%. And what you get basically is that the submovement number increases with cycle time. So as you go slower, you have a hard time and you cannot maintain smooth movement. And one of the examples that I use is, I think you already knew that, or if you have a child who's learned or attempted to learn to play the violin, you know that. One of the hard things about playing the violin is to get that, what do they call it, sostenuto, I think it is, the maneuver where you make a very long, slow movement and it's supposed to remain smooth and not scratch. But it's really hard to make it not scratch because we're not very good at making slow movements. So that's a limitation. So my point here is that limitations due to dynamic primitives, they reflect the software, not the hardware, or if you want, it's the wetware. So this is not a hardware limitation of human movement control. It's the way that our brain is managing them. And if there are these, yes?
Does the submovement time constant relate to the transmission delays in some measurable way?
Just repeat the question, Russ.
Does your submovement time constant have some nice relationship with the transmission delays you opened with?
The short answer, I don't know, because the transmission delays are much longer than people originally thought. If you just count for example, if the feedback delay from my foot through my spinal cord back out, that's about 50 to 70 milliseconds. So yeah, that's long, but not too bad. But some recent work from Maganaris' group, they've looked at, they actually measured the correlation from soleus to center body motion, and they got delays of 370 milliseconds. So way, way longer. So I think they're related, but I'm not sure. Well, I mean, one of the things that does appear to be a constraint is there seems to be an interpulse interval, sort of refractory period between pulses that ballparks out at about 100 milliseconds. And that's very similar to one of the core frequencies that you see in EEG. So it's a coincidence, perhaps, but looks like that. So if there are these limitations, then maybe we need to know about them if we're going to try to implement human-robot physical interaction. And this is some other work that we've done. So I don't know if you know it, but there are certain patterns that dictate how you move. So when you make curved movements, you slow down on the curves. It may seem obvious, but anyway, it follows in what's called the 2/3 power law. That is, the angular velocity is the 2/3 power of the curvature as a function of time, or you can alternatively express it as tangential velocity is a function of radius of curvature to the 1/3 power. But it's a power law relation between speed and curvature, and it means you slow down as you go around the corners. This is an observation that's been debated back and forth since 1982, and it's still being debated as to, is it real? Is it of mechanical origin, of neural origin? Anyway, but it's fairly robust. So the point to be noted is that I typically don't have robots move in this way. And so the question that we asked is physical cooperation with a position control robot more effective when it exhibits this pattern of relation between speed and curvature? So here's the experiment that was performed. The robot in this case was a haptic master. It's a 3D haptic interface robot. Drew an elliptical path, subject held onto it, and the subject was asked to maintain contact with minimal force. Don't let go, but keep the force as small as possible. And what you find is we then did the following. So this is the biological pattern. The color code indicates the speed. And as you can see, the biological pattern is to speed up on the straighter parts and slow down on the curved parts. We compare that with constant speed. Compare that with an exaggerated biological version. That is, you sped up a lot on the straights and you slowed down a lot on the curves. And then the reverse, where you slowed down on the straights and whipped around on the corners. And then basically saw what subjects could do. And what you find is that experimentally, here's the standard, and they do much, here's the constant, much poorer with the constant. Here's the reverse, and it's just awful. So subjects have a hard time with this. Summarizing the behavior, basically biological pattern is better. This is biological, constant, exaggerated, and reverse. And we as Pauline Maurice, who's now, she's at CRNS, but anyway, Pauline went back and asked and trained subjects with, I believe, the constant speed profile. And with training, they could improve relative to the naive behavior, but they never got better than even when they asymptoted, they never got better than with the biological profile. So at a minimum, we should be paying attention to these quirks of biological behavior because they may help us understand how to make robots better collaborate with humans. So let me see, do I have to? I'm going to try this. I may not have enough time, but we'll see what goes on. I think that there's some important theoretical issues that we should be aware of. So first of all, the key idea here is to repurpose electrical equivalent circuits. And that's not that big an idea because that's not that hard initially because voltage and current have analogs in all domains, and so we can take advantage of that. However, there is a problem, it's not a big one, that the components don't always form circuits. So in electrical circuits, you have a clear circuit. Mechanical stuff, not always. Fine, we'll just call them networks and not require the closure that you get from a circuit. And if you look at network physical system models, they're versatile. Virtually every work I've seen on advanced control assumes a state-determined representation. State-determined representation and network models map one-to-one. The thing that's interesting, though, is that network physical system models are highly structured. And if you constrain the connectors between the pieces of a network model to be power continuous, that is, satisfy energy conservation on an instant-by-instant basis, then you can prove that the connections have to be linear, independent of nonlinearity of the things that they're connecting. And that's what leads that's what, for example, leads to Telegon's theorem. That is the orthogonality of voltages and currents and forces and so on. So this is highly structured. Okay. One problem that I ran into in trying to see if we could find a generalization is that voltage and current sources are not sufficiently general. So for example, if I think of mechanical stuff, position or configuration plays a fundamental role, and I can't necessarily get configuration from velocity because they're different kind of objects. Angular velocities from a vector space, finite angular rotations do not. Okay, that's an easy thing to solve. Just allow for more versatile sources and characterize the two different network types by the connection rather than the source. Easy enough. Another problem is that the alternative operational forms, that is the input-output form, may or may not exist in the nonlinear case. So for example, the admittance form I've assigned to be the one with motion out and force in, but you might not be able to invert that. And the impedance form is the one with motion in, force out. So in general, these operators may have no defined inverse. Okay, so that just says choose the operational form more carefully. And for example, if I looked at the manipulator mechanics, this is the standard equation for a rigid body open chain serial manipulator. And essentially, you can think of this as there's a source term, which is the combination of actuators. There's an inertia, which adds up all the forces. And this is the external force plus all the other forces add up to give you the motion, which is in terms of either position or configuration or its rate of change or whatever you want. So the operational form is well defined. Notice that that also comes with this this is where the summation of nonlinear impedances comes from. It's just the inertial object adds up forces. It's kind of a trivial observation almost. But another important thing is that the type of network, meaning whether it's a common motion or a common force network, affects what kind of invariance you should have. Now, invariances are extremely important properties of physical systems. Don't know if you know about Noether's theorems. For example, energy conservation is consonant with time translation symmetry. Invariance in a time translation requires energy conservation. Okay, well, in the context of robotics, we'd probably like to have translation invariance. That is, if I translate the reference frame, I do stuff over here, or I do stuff over here, I'd like to have the interactive behavior not change. Now, that might be challenging if I have a fixed-base robot. I can't get that if I go out beyond the reach of the robot. Maybe a mobile robot could do better, but whether it's easy to do or not, it's a useful thing to have. Okay. It's very tempting to think of dealing with interaction in terms of controlling force. So here the idea would be I'm going to specify a nominal force that seems natural, and I'll specify an interactive dynamics and impedance that modifies that force. And here's the dynamic case, and here's a static case, for example, like a spring but with dynamics. If I now translate the coordinates and I define a new set of coordinates, the problem that I run into is that now the source term depends upon the interaction term. So I do not have invariance. The translated force source varies with the stiffness and the reference frame. And so now I've messed up one of the major benefits of the equivalent circuit, which is the separation of the forward path and interactive dynamics. Instead, if I look at nominal motion control, I specify a nominal motion. Write my impedance as force is an operator on the deviation of actual from nominal motion, like a spring written this way. Now I translate the coordinates, and I wind up with the representation as translation invariant. So I've kept the separation of forward path and interactive dynamics. So I argue that this invariance favors specifying a nominal motion, not a force. So if I think about actuators like muscles, they're interface objects, but fundamentally, I want to represent them as a nonlinear equivalent network that is this combination of interaction with forward path dynamics, but the source term should specify motion, not force. So even if we think that force is the right way to go, I think the argument is that it shouldn't be. So let me finish up. I'm probably running out of time. Basic message is dynamic primitives may account for human performance, not just motion primitives, but interaction primitives as well. Representing both of them facilitates this compositionality. And to do that, I'm going to use an equivalent network. The dynamic primitives may also account for human limitations, and I think understanding those limitations could be important when we go look at physical human-robot interaction. And this has been supported by a number of different sources and a number of people who have done the real work, and Hermano Krebs and Dagmar Stern are prominent among them. So thank you.
Any questions? And please take the mic.
Thank you, Neville.
Now I'm frightened.
I don't recall you saying the word stability at all. In terms of if you compose two stable motions and they're nonlinear, can you guarantee that they'll be stable when you compose them? Or as you think of like more complicated, like your soccer examples, how do we get dexterous robots that can build these primitives and not fall down? That kind of.
So the first thing is that if you have two objects that interact, and you so if they have a fixed nominal reference position and you connect them up, in general they can become unstable, right? Because the dynamic interaction forms a feedback loop. However, one of the ways that you can completely guarantee stability is to make the system look passive, make the impedances look passive, and that's been known since, I don't know, for quite a while, and it works. So passivity is conservative in the sense that it may limit what I do, but on the other hand, I get guaranteed the coupling and contact do not compromise stability. One of the limitations, however, is that to achieve passivity of the port impedance, I may have to limit my feedback gains. So for example, it's tempting to think that I could use a force sensor with feedback to reduce apparent inertia, right? Use the force sensor to say, get the motors to help me move in that direction. That's okay, but you'll violate passivity if the loop gain of the force loop is bigger than 1. And the loop gain of 1 is pathetic. So you can solve the stability problem, but there are limitations.
So thanks for the talk. So I had a question about the cloth part and all the coupling and the fact that impedances add. So I understand all that. Then how do you, but when they add, let's say you want to actually control the cloth to do a specific thing. So you can add them, but then the question is, how do you actually pick the impedances? And then even though they're independent, you add them, they both affect the actual motion of the object. So how do you sort of deal with that when you're doing manipulation, for example?
That's a great question. We're working on it. So, so the first thing is, how do you make them not interfere? One of the ways is, that we're working on right now is, if I specify an end effector impedance, I can project that impedance into the configuration space, and then I can find the null space of that impedance. So think of in terms of stiffness. Rather than finding the null space that, say, minimizes kinetic energy, I find the one that doesn't interfere with my endpoint stiffness. We're at present looking into whether or not you can do that for both endpoint stiffness and damping and so forth, and stay tuned. We're working on it. So null space, use the null space is one way to go. Another way which we've been looking at is, how do you select impedances? Well, fundamentally, I think that should be a sort of a learning or optimization problem. And recently started working on trying to see, can we use optimization to learn the appropriate impedance? So I want to optimize not just trajectory, not just force, but the relation between them. And one of the nice results is that we did that in the context of having a composition of an end effector impedance plus a joint impedance. So the joint impedance we left alone. It was just there to stabilize the configuration. But the optimization then figured out the optimal endpoint impedance and endpoint trajectory to overcome the corruption that you get from the joint space. So it looks like that can work. So essentially, you start with modules, and then you cheat and use optimization to make the modules not interfere with each other.
Neville, thanks. Good talk. Always I learn something new. When we talk about the leg compliance and impedance, obviously one thing is that we can better handle the uncertain terrain stuff. To what extent in the impedance research community have looked at how we can actually better handle the uncertainties, characterizing some of the characteristics, quantifying the uncertainties or whatever? Is there any way that we can actually find the best impedance that really makes sense, and then better handle kind of foreseen uncertainties?
Yeah, that's it. Again, a great question. I think the way to, so I don't know the answer. I think the way to do it is cast that as an optimization problem again. So if I have a characterization of the uncertainty, if I put into my cost function something that penalizes the force and the motion at the same interaction port, then that's the optimization essentially gives you an impedance. I don't know if anybody has actually worked on that, but I think that's the way I would try to go. Essentially, cast it as a robustness problem and optimize the impedance for robustness. But I don't know if it. I don't know how well it works. And one of the other things to realize is all these equations look great, but you have to check whether you actually get the compositionality. And let me see if I can. We looked at does compositionality of impedances actually work in practice? So this is Baxter. Baxter was asked to simulate a spring, and simulate a spring with the left hand, the right arm, the left arm, and then both them both together, and see if you get the superimposition. And for stiffness, it looks great. Percent errors are down in the 1% or better, so looks wonderful. Then we actually looked at the dynamic terms, like the damping and inertia, And what you see is that with damping, we're not getting very good rendering of damping because of static friction. And the error from the sum is not too bad, but it's not as good as we got with stiffness. Then you go look at the rendering of inertia, and it's terrible. We can't render the inertia correctly, and when we look at the sum of the inertias, that's off by 50, 60%. The inertias, I mean, the inertias should add up, but they don't. And I think what's going on is, and this is what prompted this, is that we have the inertia measured for each arm independently, but they're not actually moving in the simple straight line that we want them to. There's a bit of wiggle going on. Then we bolt them together, and neither arm is moving in the straight line that it used to move in. So this is a case where the uncertainty of the actual kinematic motion messes up the compositionality of the inertia term. So it's a real problem. I'm not sure. I think the best way to go is try to include that in the learning or optimization process, but don't know that yet.
I'm going to ask a question myself. I'll use the opportunity. So you said in the talk that when you look at sort of a human limb or any sort of biological system, there's tremendous complexity in how it's structured, but when you try to model it as a dynamic system, it's highly simplified, right? So there's like, we get behavior that can be explained with a dynamic system of order 2 or order 3.
Order 2.
And I wanted to get your opinion as to what degree that's also a byproduct of the fact that maybe just like evolution has favored the creation of systems that they have simpler behavior so that they can be controlled, and what that says about the kind of mechanisms we use today to fabricate robots, for example.
So first of all, my answer to that is complete speculation. I don't have a
That's what I'm asking.
so in the first place, the thing that's the simplest is the interactive behavior. So you push on the limb and measure the force evoked by displacement. If you look at that for a single muscle, it's first order. If you look at that for muscles connected to the skeleton, even though you got lots and lots of muscles, the behavior is basically second order. And maybe you can find, for example, we did this measurement on the ankle, and there's a difference between your ankle impedance when you're standing and your ankle impedance when you're sitting. And there, that difference shows up as a small deviation at about 3 hertz. You get slightly third order behavior at that point. So the interactive behavior is simple. The forward path behavior is horribly complicated because you've got time delays, you've got multiple feedback delays. The muscle itself is at least second order response to the isometric force response of a muscle to a single nerve impulse is at least second order. It seems to be second order real, like with real poles, no resonance. But you then add the fact that you have a feedback loop through the spinal cord with about a 20, 30 millisecond delay. You've got a feedback loop through the cerebellum with about 100 and something millisecond delay, and through the cortex with about 150. It's a mess. But the interactive behavior stays simple. Is it likely that, so I think one of the things that I think is going on, particularly with spinal level feedback, is it's doing what I would call muscle management. So you're managing the muscles so that it looks simple no matter what. Muscles fatigue, by the way. They get hot, they fatigue. All of that changes their behavior dramatically. Yeah, but not catastrophically. And I think that what the local feedback loops are doing at the lowest level is managing the system to be something simpler for the next level up. But like I said, that's speculation. But your biomechanics co-evolved with your neurons. So it would not be surprising if they had evolved to be compatible with each other. Your question about anything we could learn about for designing robots, my sense is give me robots with tunable low impedance. Nice, smooth, variable stiffness. A number of people are working on that. It's not easy, but it's doable.
Any more questions?
So, if I understood, it sounds like you're defining impedances in terms of the task space, maybe exclusively. How would you incorporate configuration space restrictions like torque limits, let's say, into this framework?
So in the first place, yes, I start by saying I want an end effector behavior, and then I add in configuration space behavior. But it's not difficult, and it's been done before, to incorporate things like joint limits by adding in essentially repulsive impedances. Imagine you set up in configuration space a repulsive force field that says avoid this configuration. That not only can be done, but it has been done some time ago. You can do the same. That's not, finding the shape of the force field that you have to set up is not trivial, but it's computable. And you can also avoid self-collision with multiple arms. There's this problem. You can again map that into a nominal repulsive impedance, and I believe so. I believe that's been some of the KUKA work has done that, right? So yes, you can factor that in. You add all those pieces, and your computation gets nastier. But because it's modular, you might be able to manage that better than trying to solve one giant optimization problem.
I ended up with a microphone, so I'll ask one real quick. So you're convinced about the mechanical contact having a pretty simple mechanics. What do you think about the perception of motion? So we talk a lot about these days about intuitive physics and our ability to perceive motion and understand and predict what's going to happen if boxes are falling in front of us or whatever. Do you think we're putting it through that same mostly linear
So again, this is wild speculation, but take it for what it's worth. I'm personally convinced that actually the internal representation that I use for cognition is the same. It uses the same set of dynamic objects, submovements, oscillations, impedances, maybe postures. I'm not sure if you need that one as an extra. And that's in fact the way you represent stuff. Now, how to prove that? We're working on it. But I think that's actually, I think that simplifies some of the cognitive operations that need to be performed. Part of the challenge is, well, what do you mean by cognition? Okay, well, I'm going to say prediction is part of cognition. Okay, well, I think we can make a case that prediction used in motor behavior could be based on these primitives. Things like overcoming a time delay, that requires prediction. But I mean, so if I can predict far enough to overcome my own internal time delay, maybe I can extend that to saying, what would happen if I was to try and model two humans interacting? Well, I can model them both as having these primitives and stick them together. As you can tell, I'm hand-waving a bit, but I think that, I'm willing to bet that that's a core part of the cognitive representation of objects like me.
All right, I think that it's time, so thank you very much.